Welcome to the deep dive. Today we're tackling a really crucial part of mineral processing.
We are indeed.
The unsung heroes, filtration cloths in hydrometallurgical processes.
Absolutely. They do so much work behind the scenes.
Yeah, think about how we get those valuable metals out and, ditch the waste.
A huge part of that separation, the solid-liquid separation, it comes down to these fabrics.
These specialized fabrics.
Exactly. And, it might look like just a piece of cloth.
Right.
But it's actually a pretty complex engineering challenge.
Because the conditions inside those hydrometallurgical circuits, they're wild, right?
Oh, incredibly dynamic. You're dealing with a whole spectrum of chemical environments, pH levels.
And the particle sizes vary hugely.
Massively. Plus the sheer amount of material, the tonnage.
And temperature fluctuations. Can't forget those.
Definitely not. Big temperature swings are common.
Okay, so you can't just grab any old fabric off the shelf.
No way. It just wouldn't work or wouldn't last. There's really no magic one-size-fits-all solution here.
Right. That's why in this deep dive, we really want to focus on the fundamental principles, the things that guide selecting the right filtration fabric for these specific applications.
Yeah. Specifically hydrometallurgy. And we've got some great material to draw on here.
We do. It should help us break it all down.
And just to give a roadmap, we'll be looking at the key things manufacturers can actually control when making these fabrics.
Okay, like what?
Well, everything from the basic polymer, the plastic fiber itself, through the type of yarn, how it's woven, even the final treatments they put on the surface, coatings and things like that.
Got it. Okay, let's get into it then. The absolute foundation.
Yeah.
The polymers.
Right.
Our sources say synthetic polymeric fibers are pretty much dominant now. Why is that?
Well, the beauty of synthetics is really that you can fine-tune their properties, almost design them at a molecular level.
Okay.
Think about those aggressive conditions we just mentioned, chemicals, heat, stress.
Yeah.
You need materials that can actually withstand all that. So by picking the right polymer from the start,
You're building in resistance.
exactly, you're building in compatibility with that specific operating environment. There's a figure 1 in our material.
I saw that.
It really shows how pH and temperature dramatically impact the mechanical strength of different polymers.
So the wrong choices falls apart.
Pretty much. It could degrade really quickly. Total filter cloth failure.
Okay, so it's not just catching solids. It's about surviving.
Survival is key, and the material points to 3 main players, polymer-wise.
The common ones.
Yeah, the ones you see most often. Polypropylene, that's PP. Polyester, PET, and polyamides, PA.
And they're popular because they hit that sweet spot. Cost versus performance.
That seems to be the case, yeah. They offer a good balance.
Okay, can you give us a quick comparison? PP, PET, PA. How do they stack up?
Sure. So generally speaking, if you look at mechanical resistance, just how tough they are physically,
Right.
polyamides, PA, tend to be the strongest. Then PET, then PP. And you see a similar pattern with abrasion resistance, how they handle rubbing and wear. PA is usually best, then PT, then PP again.
But what about cost? That's always a factor.
Always. And here, the order flips. Polypropylene, PP, is typically the cheapest.
Right.
Then PT is sort of mid-range, and polyamides, PA, are generally the most expensive. Table 2 lays that out pretty clearly.
So there's that trade-off right away, strength versus cost.
Exactly. If your process is really rough, lots of physical stress, maybe abrasion, even though it costs more upfront, that polyamide fabric might be the only way to avoid constant replacements.
And the downtime that comes with that? Costly.
Very costly. So yeah, sometimes paying more initially saves money in the long run.
Makes sense. What about getting the solids off the fabric?
Yeah.
Cake release, right?
Yes. Crucial for efficiency.
How do they compare there?
Well, the material suggests that polyamide PA generally gives you better cake release compared to PP and PT.
And why is that so important?
Because if the cake sticks, you need more effort to remove it, maybe harsh cleaning.
Which takes time.
Takes time, lowers your throughput, and can even contaminate the next batch if it's not cleaned properly.
Okay, so good cake release means faster cycles, cleaner operation.
Exactly. So again, it comes back to priorities. What does your specific application demand most? Durability, low initial cost, or is that super efficient cake discharge the key?
It's always a balancing act, isn't it?
Always.
Okay, so we've got the basic materials, the polymers. Now, how are they actually turned into the fibers, the yarns that make the fabric?
Right, the yarn types. The source material talks mainly about two kinds, monofilament and multifilament.
Monofilament and multifilament. What's the difference?
Okay, think of monofilament like a single solid strand, kind of like fishing line, but in various thicknesses, maybe 20 to 1,000 micrometers.
Okay, one thick strand.
Pretty much. Now, multifilament is different. It's made of lots and lots of very fine filaments, tiny little threads, all twisted together to form one yarn. Like imagine a bundle of super fine sewing threads.
Got it. Single strand versus a bundle of fine strands. And how does that affect the filter fabric?
Oh, it leads to really distinct performance. Monofilament fabrics, because they're made of those smooth single fibers, they tend to give you exceptional cake release.
Because there's less for the cake to cling to.
Exactly. Smoother surface, less area. So the cake comes off easily. They're easier to clean, less likely to clog up.
Which means higher throughput, faster processing.
Often, yes. And figure 3 shows something interesting too. With monofilaments, the cake itself builds up and becomes the main filter layer.
Cake filtration.
Right. And that can actually improve efficiency as the cake forms. Plus, they tend to last longer, especially if your particles are all roughly the same size. Less prone to blinding in that case.
Okay, that sounds pretty good. So why would you ever choose multifilament then?
Well, multifilaments have their own strengths. That complex structure with all those fine fibers twisted together gives them greater mechanical strength. And they provide a finer surface filtration.
Meaning they catch smaller particles right away.
Exactly, right at the fabric surface. The actual pore size of the fabric itself is doing more of the separation work. That's often called depth filtration, also in figure 3.
Like a dense net, trapping things inside.
Kind of, yeah. But that same structure, the dense web that's good at catching fines,
makes them more prone to blinding, clogging up.
Precisely. All that surface area, the complex network, gives particles many more places to get stuck permanently.
So your flow rate drops over time?
It tends to, yes. It's a classic trade-off.
Okay. The material also mentions non-woven fabrics, needle felts, spun materials. How do they fit in?
Right. Non-wovens are made totally differently. No weaving involved.
How then?
Fibers are basically bonded together. It could be mechanical, like needle punching, or thermal or chemical bonding. It creates a random sort of three-dimensional structure.
And how do they perform?
They can be very effective for filtering fine particles, and often they're a lower-cost option.
But there's a catch.
Usually. The source notes that trade-off again. The better they are at capturing tiny particles, giving you really clear filtrate, the more likely they are to clog up quickly and not last as long.
Clarity versus lifespan.
Pretty much. For really, really fine stuff, sometimes they even add a membrane layer, but that can slow down the flow rate even more.
So it seems like you're always juggling these competing factors, maybe combining approaches.
Absolutely. The material mentions hybrid cloths.
Mixing mono and multi.
Yeah, using both monofilament and multifilament yarns in the same fabric. Trying to get the best of both worlds.
Like the strength of multi with the cake release of mono.
That's the idea, trying to find that optimal balance. Ultimately, picking the yarn type really impacts, your filtrate clarity, how long the cloth lasts, and your overall throughput. Figure 4 gives a general comparison there.
And it's important to remember lab tests versus reality, right?
Hugely important. The material stresses that point. The pore size you measure in a lab under, say, 200 pascals of air pressure can be very different from the effective pore size when that fabric is under high pressure, wet, in a real hydromet process.
So field testing is key.
Crucial. Pilot studies, field trials, that's where you really see how it performs.
And the source even brings in some fluid dynamics basics. Darcy's law.
It does. Equation 1, the basic Darcy's law for flow through porous media.
What's the takeaway there?
Essentially, to get high flow and low moisture in the cake, you want low flow resistance from the fabric and low viscosity in the liquid. Pretty intuitive.
Makes sense.
Then equation 2 modifies it for cake filtration. And a key factor there is the specific resistance of the cake itself, alpha.
And that depends on
how compressible the cake is and how thick it gets. So selecting the fabric and setting up the process involves trying to minimize that resistance while still catching the particles you need to.
Right. Table 3 sort of summarizes the pros and cons of each yarn type for different goals, doesn't it?
Yeah, it's a handy summary. Whether you prioritize low moisture, low resistance, clarity, or cake discharge, it points you in a general direction based on yarn type.
This really shows selecting the yarn isn't trivial. It's about understanding the whole physics of the filtration.
Deeply understanding it, yes.
Okay, moving on, we have the yarns. How are they put together? The weaving patterns.
Right. The weave determines the cloth's macroscopic structure.
Macro, meaning the bigger picture.
Exactly. How the warp yarns the lengthwise ones and the weft yarns the crosswise ones interlace.
And that affects.
A lot. Pore size and shape, surface smoothness, even how it looks, and critically, its mechanical strength and stability.
Okay. And the source mentions different types. Plain, twill, satin.
Those are the basics, yeah. Plain weave is the simplest, 1.1. One warp over one weft under the next, like a basic checkerboard, very tight.
Okay. And twill, like in jeans.
Exactly like jeans. That diagonal line, that's usually a 2.1 or 3.1 weave warp, goes over 2 or 3 wefts, then under 1.
And what does that do?
It generally makes the fabric more pliable, flexible than plain weave, and it affects abrasion resistance and the open area, the porosity.
Got it. Then the satin weave?
Satin involves longer floats. A warp yarn goes over several wefts, maybe 4, 5, or 6, before ducking under 1.
Creating that smooth, shiny surface.
Precisely. And that smoothness, as we talked about before...
Helps with cake release.
Huh.
Especially for fine particles.
Exactly right. Figure 5 gives a nice visual of these basic weaves.
I see. The material also mentions double layer weave, DLW. Sounds more complex.
It is. You're essentially weaving 2 separate fabric layers together at the same time.
Why do that?
It gives you enhanced mechanical strength and much better dimensional stability. It holds its shape better under stress.
Which is it good for?
Really demanding applications like horizontal vacuum belt filters, HVBFs, they see a lot of tension and wear.
Makes sense.
Plus, you can design DLW smartly. Maybe a tight top layer for fine filtering and a more open bottom layer for good drainage.
Clever. So how does picking the weave ultimately change the filtration performance?
It has knock-on effects everywhere. If you need maximum flow rate,
go for open weaves, like twill or satin.
Generally, yes, they offer higher permeability. For catching particles effectively, the tightness and the specific pattern matter.
And for resisting blinding, clogging.
Smoother weaves, like satin, tend to be better because particles adhere less.
And strength.
Weaves like twill, and especially DLW, with their more robust structure, usually offer better mechanical strength and abrasion resistance. Better longevity in tough conditions.
And cake release, again, is linked to surface texture.
Absolutely. Smoother weave, easier release. Table 4 kind of sums up these general trends for different weave types. It shows the trade-offs.
It really drives home that every single choice, polymer, yarn, weave, it's all interconnected.
It's all deliberate engineering with real consequences for performance.
Okay, last main piece. Finishing and add-ons. What happens after the weaving?
This is where you can really fine-tune things, add specific properties.
Like what?
Well, thermal treatments are common, heating the fabric carefully near the polymer's melting point.
What does that achieve?
It can actually shrink the pores slightly, increase the surface area, potentially improving particle capture and cake release.
Interesting. And calendaring. Figure 6 shows that. Looks like rollers.
It is. Passing the fabric between heated rollers under pressure,
So true.
creating really consistent pore openings, and giving it a very smooth finish on one side. Better cake release again, more controlled properties overall.
And heat setting. You mentioned that earlier.
Right, heat setting is critical. It's another reheating step, but its main purpose is to lock in the fabric's dimensions, improve stability.
So it doesn't stretch or deform easily during use.
Exactly. Especially important if it's going to face high pressure, stretching, abrasion. It actually changes the polymer structure slightly for better physical and thermal properties.
Okay. And beyond heat treatments.
Oh, there are surface treatments, chemical additives.
Yeah.
You can make fabrics repel oil, oleophobic, or water, hydrophobic, or improve stability even further.
The mechanical things.
Sure. Adding reinforcements, backing layers for extra strength or support, using special closures or edges to make installation easier on the equipment.
Wow. It's incredible how many levers they can pull to customize these fabrics.
It really is, tailoring it for a very specific job.
So as we wrap up this deep dive,
Yeah.
what are the main takeaways for listeners thinking about filtration cloths?
I think the biggest thing is that selection is absolutely not simple. It's not off the shelf. You have to understand your specific process conditions first. The pH, the temperature, the particles, the flow rates, everything.
And then match the fabric properties to those conditions.
Exactly. And know how each choice interacts. The polymer sets the basic compatibility and cost. The yarn type dictates that balance between clarity, flow, and cake release.
Monofilament, multifilament, non-woven.
Right. The weaving pattern controls the structure, affecting strength, flow, blinding.
Plain, twill, satin, DLW.
And then the finishing treatments fine-tune everything else.
So it's a highly tailored process.
Extremely. There's no single best fabric overall. The optimal fabric is the one engineered or selected specifically for that unique hydrometallurgical duty.
You need to consider all these interconnected factors together.
Holistically, yes. To get the best efficiency, the best recovery, and ultimately the best process economics.
It really gives you an appreciation for these materials. They look simple, but they're critical tech in complex systems.
They truly are, and the field keeps evolving, you know? New materials, new fabric designs, constantly pushing what's possible in separation.
Fascinating stuff. Thanks so much for breaking down this complex topic today.
My pleasure. It was great discussing it.